Welcome to the third part of the video on Unit 3 Computer Vision Future Based Alignment and Motion Estimation. I am Dr. K. Priya, Assistant Professor, Department of PCB, Government College of Engineering, Tamil Nadu. Vanishing points, a man-made scene with a lot of rectangular objects such as boxes or round walls. Intersect the 2D lines corresponding to 3D parallel lines to compute their vanishing points. Use these to determine the intrinsic and extrinsic calibration parameters. The diagram shows the calibration from vanishing points. The first diagram, it shows any pair of finite vanishing points xi cap, xj cap, which can be used to estimate the focal length. And the part B, it shows the orthocenter of the vanishing points. That is, you drop perpendiculars with the three lines and they meet at a center, and this is called as the orthocenter. So orthocenter of the vanishing point triangle gives the image center of the image C. Assume a simplified form for the calibration matrix K where only the focal length is unknown. So xi cap will be this matrix xi minus cx, yi minus cy, then the focal length, which is approximately equal to r into pi, which is equal to r. So the pi is three sets of points like this. Either first value is 1 or that to 0, or the middle and the last one is 1. Ri is the ith column of the rotation matrix, capital. The columns of the rotation matrix are orthogonal, therefore xi minus cx into xj minus ex plus yi minus cy, yj minus cy plus f square equal to 0. So we can obtain an estimate for f square. So it's also possible to estimate the optical center as the orthocenter of the triangle formed by three vanishing points. It is more accurate to re-estimate using non-linear least squares. To determine the focal length f and opticenter UC, VC from the image of cubes or buildings, any buildings, this is the way how you find out your vanishing points. So x, y and z directions. So where xi is equal to, so all the places you are replacing by 1. So you have different combinations of points correspond to vanishing points that are the scaled version of the rotation matrix. So UV1 F in the diagonal and the last value is 1 UCVC, then rotational matrix or translation matrix into X. So this is the final matrix equation for this vanishing point determination. So orthogonality conditions on the rotation matrix capital R, where your Ri and Rj orthogonality will be giving you the del Ij. So ui minus uc, vi minus vc f dot uj minus uc, vj minus vc, f, which will be equal to 0, where I and j should not be equal. So determine the uc, vc from the orthocenter of the vanishing point triangle. Then determine the f square from two equations. So we need only two vanishing points if uc and vc are known. The advantages of vanishing point calibration. Advantages, it only need to see the vanishing points, example architecture, table, etc. And disadvantages, it is not that much accurate and it need rectahedral objects in C. Rotational motion. So use pure rotation for large scenes to estimate the focal length f. So estimate f from pairwise homographies and re-estimate f from 360-degree gap. So optimize over all k, rj parameters. So most accurate way to get f is short of surveying distant points. And the picture, it shows the f equals 510 and this is f equals 468. Rotational motion. When no calibration targets are available, but you can rotate the camera around its front nodal point, then we can calibrate the camera from a set of overlapping images by assuming that it is undergoing pure rotational motion. So capturing an image and you are trying to rotate it to the next question. Now this image is being captured after the rotation of the camera. Similarly, this is the red color slot. This is the second position of the camera, little bit down towards the roof, and this is the rotated next page. So similarly, rotating the cameras to different position, you capture different pictures in the same area. When images are taken with wide angle lenses, it is often necessary to model the lens distortion such as radial distortion. We have two types of distortions of radial distortion. One is barrel distortion, the other one is pin cushion distortion. And radial distortion equations, x cap and y cap, which is equal to x into 1 plus k1 r square k2 r power 4. Y cap equals y into 1 plus k1 r square plus k2 r power 4, where r square is equal to x square plus y square, and k1, k2 are radial distortion parameters. A lot of different ways to estimate the radial distortion parameters are available, and one of the simplest and most useful way is take an image of the scene with a lot of straight lines, adjust the parameters until all of the lines are straight. So like the plumb line method, you have to use it so that every line turns to be a perpendicular, or a plumb line method that is vertical, horizontal, everything is to be checked there. Radial distortion. Another approach is to use several overlapping images and to combine the estimation of the radial distortion parameters with the image alignment process. So we can add another stage to the general nonlinear minimization pipeline method when a known calibration target is used. Sometimes we need more general models of lens distortion, and the general approach of either using calibration rigs with the known 3D positions or self-calibration through the use of multiple overlapping images of a scene, and it can both be used. Post-estimation. So post-estimation means we estimate an object's 3D pose from a set of 2D point projection. So we use both linear algorithms and iterative algorithms for post-estimation. So first of all, we can see about the linear algorithms. It is the simplest way to recover the pose of the camera, and it form a set of linear equations analogous to those used for 2D motion estimation from the camera matrix form of perspective projection. So the equation for xi and yi, where xi, yi are the measured 2D feature locations, and xi, yi, zeta, capital Xi, yi and zeta are known 3D feature locations. So solve the camera matrix capital P in a linear fashion, multiply the denominator on both sides of the equation. So denominator d, which is equal to P20 xi, P21 yi plus P22 zi plus P23. In linear algorithms, you can also use direct linear transform, that is DLT method. At least 6 correspondences are needed to compute the 12 or 11 unknowns in P. More accurate estimation of P can be obtained by non-linear least squares with a small number of iterations. P equals K into R slash T. R is the rotational matrix appended with the translation matrix T. Recover both the intrinsic calibration matrix K and the rigid transform R, T. Capital K and capital R can be obtained from the front 3 cross 3 submatrix of P using RQ factorization. In most applications, we have some prior knowledge about the intrinsic calibration matrix K. Constraints can be incorporated into a non-linear minimization of the parameters in K and R, T. In the case where the camera is already calibrated, the matrix K is known, so we can perform post-estimation using a few as 3 points. So an example for post-estimation linear algorithm, this is the projection points Pi and Pj, and the distance between the Pi and Pj is given by Dij, where the Di is the distance of the projection point I from the center. Similarly, Dj is the distance between the projection point J and the center. And the angle subscribed between the two projection points are theta ij. So Pi is denoted as xi, yi, zi, wi. Similarly for Pj, It is xi, yj, xj, yj, zj into comma wj. So xi cap, it gives the unit directions of xi, and the visual angle theta ij is between any pair of 2D points xi cap and xj cap. It must be the same as the angle between their corresponding 3D points also, pi and pg. That is the projected points in 3D. Xi cap is equal to n into n of k inverse xi, which is equal to k inverse xi divided by modulus of k inverse xi, where pi is equal to di into xi cap plus c. And the cosine law gives the distance between the two projection points dij square is equal to di square plus dj square, the individual distances between the projection point and the center, minus 2 di dj cos theta ij. Theta ij is the angle comprised between the pi and pj, and which is equal to modulus of pi minus pg square, the projection points I and j. We can take any triplet of constraints and using Sylvester resultants to obtain a quadratic equation in di square, that is gij of di square is equal to a4 di power 8, a3 di power 6, a2 di power 4 plus a1 di square plus a0, which is equal to 0. So this is a quadratic equation in di square. So give 5 or more correspondences, we can obtain a linear estimate using SVD, single vector decomposition for the single value decomposition for the values of di power 8, di power 6, di power 4, di square. So computed the di power 2n plus 2 divided by di power 2n to estimate the di square and di. We can generate a 3D structure consisting of the scaled point directions di into xi cap. So use 3D alignment to obtain the desired pose estimation. Minimal PNP solutions can be quite noise sensitive, so it also suffered from bas relief ambiguities. So use a linear algorithm to obtain an initial pose estimation, then optimize this estimation using the iterative algorithm. The most accurate and flexible way to estimate the pose is using nonlinear least squares. So the projection equation xi, which will be a function of pi r t k, where rotational matrix, translational matrix and k. Iteratively minimize the robustified linear reprojection errors. So your ENLP equation is given, non-linear projection. And it's an easier way to understand and implement version of the above non-linear regression problem. So it can be constructed by rewriting the projection equation as a concatenation of simpler steps. So the diagram shows a set of chained transforms for projecting a 3D point pi to a 2D measurement xi through a series of transformations f, each of which is controlled by its own set of parameters, and the dashed lines, it indicate the flow of information as partial derivatives are computed during a backward pass. So once the internal camera parameters are known, you can compute the camera pose. So when you do so, when your internal camera parameters are known, and you will calculate your 3D point values. So application mainly it is superimposing the 3D graphics over to a video. So how will we initialize this parameter r and t? So for that, solve the orthographic problem. So you iterate it, use the interpoint distant constraints, and you find out your u and v. So ui, this is the value of it, and xi will be modulus of your xi, and then dij square will be equal to modulus difference between your xi and xj. So this is your expansion of it. So solve the set of polynomial equations in xi2. So previous initialization techniques we used as vanishing points and planar patterns, and other possibilities are also available through the lens camera control and by differential updating, and also you can use more than 3+ points using linear methods. Then the next topic is triangulation, that is 2 points we projected. So given the projection pi of unknown 3D point x in 2 or more images with known cameras mi, and then we can find easily the x. So why is the calibration here important means, you have to find out how much it is calibrated and it is getting focused with X. So rays in principle it should intersect, but in practice usually don't exactly due to noise or some numerical errors. So find the shortest segment between the rays and set X to be the midpoint of the segment. So this is the segment which you are making, and this is the midpoint of this shortest distance, that is your X. So this is a 3D point triangulation by finding the point P, which is bisecting this line that lies nearest to all of the optical rays Cj plus Dj Vj cap. So to find X, minimizing the distance of P1 M1x square plus distance of D of P2 M2x the whole square. So this is how the linear optimization is made. So your P1, P2 which is being equated to 0, and the cross product of it, this is a general equation of it. So you do that, and afterwards you get two equations for each camera for 3 unknowns in X. So give some points in the correspondence across 2 or more images taken from calibrated cameras. So you get a set of values of uj, vj and compute the 3D location X. So in the first method, intersect the viewing rays in 3D and then minimize the value. So this is how argument minimizing the X. So X is the unknown 3D point, Cj is the optical center of camera J, and Vj is the viewing ray for pixel uj, vj, and Sj is the unknown distance along Vj. And the advantage is it is geometrically intuitive. And the second method is by solving the linear equation in X. So the advantage of using this method is it's very simple. You have 2 sets of equation and you solve it out and you find out the value for X. And the third method is non-linear minimization, and the advantage of this non-linear minimization is it is most accurate and you have image plane error avoided. The next topic is structure from motion. So you have a structure to be captured, and what the way you do is fix some points around the random points around the object and you capture out the picture. So this is the capturing the structure in movement. So you have unknown camera viewpoints. So you don't know which point it has been captured. So to reconstruct the picture from all the 2D pictures to 3D, how you have to do is, that is, you must be known with the scene geometry and also with camera motion. So structure from motion, it is denoted as SFM. So the SFM, what's the issues we have is you have to reconstruct the scene geometry and camera motion from 2 or more images which have been captured from different locations around the object. So track the 2D features, you estimate the 3D features from the 2D features and then optimize it. For that you use bundle adjustment and then fit the surfaces and you recreate the 3D picture of the 2D images. So what are the steps you follow for making the recreating the structure from motion? So first you have to track the features. So detect the good features of it. There is a notable features which are like corners, line segments, etc. Then find the correspondences between the frames. So you have 2 techniques here, either Lucas Canaday style motion estimation or Windows based correlation. And step 2, that is, these are the images, how much frames you are, F is your number of frames, how many number of images you have captured in different types of motion, and this is your structures x1, x2 up to xn. And you estimate the motion and structure. So either you can use a simplified projection model as given in this method, or 2 or 3 views at a time. And step 3 is the refining the estimates. So it is done by bundle adjustment in photogrammetry. And the 4th step is you recover the surfaces from them. So if you, this is an example for poor mesh condition, and this is an example for good mesh condition which follows all the line segments here. So to recover surfaces, we have these 3 methods: image based triangulation, Stillhouse and stereo. And the problem in it is to find the correspondence between n features in f images. And what are the issues? What's the feature? How does it correspond? And how many correspondence you need for reliably computation. So in SFM problem, you have to reconstruct the scene geometry and camera positions from 2 or more images. So assume your pixel correspondence via tracking, and these are the projection models. Classic methods are orthographic, and near methods it use perspective, and practically any model is possible with bundle adjustment. And under orthographic projection, this is the image point U, and this is a projection matrix 2x3 matrix, and the scene point 3 cross 1, and the translational matrix image offset, which is a 2x1. And most generally it is weak perspective, para perspective, often. And the trick is to choose the scene origin to be centroid of 3D points, and choose the image origins to be centroid of 2D points, and allows to drop the camera translation. So U of 2 cross 1 will be equal to pi 2 cross 3 x 3 cross 1. So structure from motion, you have different angles for a particular point, and then you minimize it, the function f of rt comma p. So given many points in correspondence across several images uij, vij simultaneously, compute the 3D location xi and camera or motion parameters. The two main variables are calibrated and uncalibrated. Sometimes you can associate the same with Euclidean and projective reconstructions. So these are the equations of how many points you need. 2 frames with 5 of 3n points, and then k frames. So structure from motion, it can be calculated from all these. You have these methods in it: 2 frame methods, factorization, bundle adjustment, non-linear least squares, and robust statistic and ransack and correspondence. And all these come under their multi-frame methods, and only this first method is here 2 frame methods. So here you have 2 main variants. One is the calibrated essential matrix E using ray directions, and the other one is uncalibrated fundamental matrix F. So this is the essential matrix, that is which deals with the coplanarity constraint. You have to solve for E using least squares SVD, and T is the least singular vector of E. R is obtained from the other 2 SVS. And the camera calibrations are unknown in case of your fundamental matrix. So you have to solve for F using least squares. You rescale it, and E is the epipole, which is still the least singular vector of F, and H is obtained from the other 2 SVs. And plane plus parallax projective reconstruction is used, and use self-calibration to determine the K. So we have 3 types of algorithm: 8, 7 and 5 point algorithm. This is the epipolar geometry of those algorithms. So in 8 point algorithm, you choose 8 values of it. So enforce your rank to constraint, take SVD of it, and throw out smallest singular values. So the point x and x dash is being calculated from 2 different pictures, and from them you solve this homogeneous equation for more than, using at least 8 or more than that matches. So this is the problem which we have in the 8 point algorithm. So we have poor numerical conditioning, and it can be fixed by rescaling the data. So in the normalized 8 point algorithm, you have to center the image data at origin and scale it so that the mean square distance between the origin and the data points is 2 pixels. So use it to compute F and from the normalized points. Enforce the rank to constraint, and for example take XVD of F, and transform this fundamental matrix back to original units. If T and T dash are normalizing transformation in 2 images than the fundamental matrix in original coordinates. The aim is to find the essential matrix or the fundamental matrix. Given 8 corresponding points to get a set of linear equations whose null space are non-trivial. If more than 8 points are used, then the system is overdetermined. We can use SVD related techniques to get the solution. The solution is unique up to a signed scaling factor. Due to the noise, numerical errors and inaccurate correspondence, E and F are most likely non-singular, then some singular constraints have to be enforced. This is a summary of the algorithm. You have to compute the essential matrix C, obtain the ratio of the components translation T. Then relative signs are determined, but absolute signs are arbitrarily selected. And rotation matrix has to be computed. Then 3D coordinates for all the visible points and a set of 3D coordinates in other camera systems are also obtained. And check the sign of the coordinates along the direction of both sets of the optical axis. So if all of them are positive, then absolute signs of T are right, else they need to be altered. And the advantage in this is it is simplicity of implementation, and the disadvantage is it is extremely susceptible to noise and hence virtually useless for most purposes. And improvement, preceding the algorithm with a very simple normalization, translation and scaling of coordinates of the matched points. 7-point algorithm. Set up least squares system with 7 pairs of correspondences and solve for null space using the SVD. Solve for linear combination of null space vectors that satisfy the determinant of F, which is equal to 0. So the special motions and structures used here are this tailored algorithms can take advantage of known camera arrangements of 3D structures. So this is a diagram which shows pure translation camera motion results in visual motion. Therefore, you satisfy the triple product condition x0 x1 e, which is equal to e dot x0 cross x1 will be equal to 0. And the other used translation, pure rotation, and dominant planar structure, all are used for. So this is the end of your part 3 of the unit 3.